Okay, here we are. We said it would happen. It happened. So now we got to deal with it. So hopefully all you guys out there are staying safe from this basic plague, I guess now. I truly hope you guys are well and healthy and all that kind of good stuff. Do let me know if you do get sick. We can discuss extensions and all that kind of fun stuff. The word "fun" there is kind of a poor choice, I would say. But anyway, I apologize for the low tech. I think my face is probably even going to be cut off here. But you don't need to see my beautiful, beautiful face. You just need to see what's on this screen and hear my words. So I'm basically recording this on my phone, on a table, in my bedroom, using my bedroom television. Yes, I have a big screen everywhere. If you've been in my office, my computer monitor is a 50-something inch. This is a 72-inch. I just have a thing for big screens. What can I say? So let's talk, or not let's, I will talk a little bit about what you should expect. So, typically speaking, the lectures will be about 50 minutes long, and I will just kind of present here like I would in front of a projector. I'm going to draw stuff, things like that. You'll have to excuse me. I'm very used to the give and take. This class requires a lot of questions, some back and forth that I won't have. And so if there's a question that you have, you should write them down as the lecture goes and essentially ask them however. You have access to asking and getting answers to questions through Piazza, okay? Me and all the TAs and all your classmates will be monitoring this. And remember, you get incentive points for answering questions on Piazza if you're in front of other answers. If you're the fifth, you probably won't get incentive points. Unless you're the first that's correct, we'll put it that way. Essentially the incentive assignments will still apply. You write the reports, just email them to me as you get them. Some people have already done that with the Akamai State of the Internet report. That's a great place to start for this class. So lots of opportunities there. But basically we're going to have about 3 lectures a week that are, again, about 50 minutes each. Today will be an exception to that, but I'll get to that. And then the 4th day will be a lab that I essentially record a short video talking about the lab, talking about your assignment, what's expected, and then usually there will be a demo. And so today it'll be a kind of a different format than that. I'm going to do about 20 minutes of lecture with this introduction material just so we can kind of get caught up. And then after about 20 minutes, what I'll do is switch to kind of a demo mode for Lab 0. And so Lab 0, I'm posting this video on Monday. And by the way, with the videos, you can essentially watch them whenever, right? You're not going to be locked into 1 hour a day, 4 days a week. You can do it that way if it works best for you. You can watch them all at once if you want. It's totally fine. But you will be responsible for the content in these videos. Essentially, I will announce homework, due dates and things like that in these videos, but they will also show up on Moodle, and I will also try to email them to you. So you'll get them in various ways. And if these videos don't help you and you feel like you can get the material other ways, that's fine. The slides are available to you, so essentially every time I post a video, I will post exactly the slides that I use for that specific video in that day. So for instance, this is week 2, day 1, and so under Monday for week 2, this is where the video will be along with the slides that I present for the 20 minutes. And then I'll talk about Lab 0, which this lab is a required lab in C, okay? But the thing there is you can use a Linux environment. If you have a C compiler working on Windows, you can do that. You can use a Mac. And essentially I provided you with 2 shells of files that I'll talk about, and then a make file, and I'll get to that as well when I do the lab demo. Let's see. So basically this is just going to be how it's going to be for the rest of the quarter. We found out that This is not going to, we're not going to return to in-person classes this entire quarter. So this is just how it's going to be. So pardon me as I get better doing this, and hopefully you guys will kind of get used to the format very quickly. And I will try and be a little bit more merciful on certain things and things like that with due dates and such. But I promise you my due dates in this class will be very, very generous. For instance, this Lab 0, I am assigning it on Monday, and of course I'm recording this early, but I think it's Monday, March 13th, if I'm not, no, I'm completely wrong. Anyway, date is wrong. I don't have my phone because I'm recording, and so I can't see the dates. Let's see, it is the 17th, so it's going to be the 23rd, I think. This will be posted for Monday, March 23rd, then essentially you will have a week to do Lab 0. Now, I might have already mentioned this. I've already done a couple of takes to try and kind of get things smoother, so I forget what I've said and what I haven't, frankly. You will have a week to do this lab, but it should not take you more than 30 minutes once you get the C stuff down. And again, I'll kind of talk about some of that stuff and demo it, but I do not expect this lab to take you very long. The major point of this lab is just to make sure that you have a C environment, that it works, and that you can turn stuff in, and then you'll turn in a zipped folder with the 2 files and your make file, and you'll turn that in through Moodle, and the first lab is like worth 60 points. So we'll get to that. So basically, the way this is going to go, again, I'm going to do a 20-minute lecture, but it's usually going to be a 50-minute lecture, and there will be three per week with a lab, and then we'll just kind of take it from there. So to get back into this material, both sections I actually finished at about the same point. So essentially, this is where we are. So we were talking about essentially the number of users on the internet, and you'll notice that the trend is really it's just growing every year. Notice this is only going up to 2018. The number of total users in 2019 and 20 are yet still higher, but it is starting to level out a little bit. But essentially, when we're talking about the design of networks, we have to consider not only these numbers, but the numbers that they eventually could be, right? More and more people are still using it, and on top of that, each person now has many devices. And as we get to the Internet of Things, where basically every single thing in your house could have its own IP address and its own Wi-Fi connection, just imagine the number of devices. I can imagine somebody having 50 to 200 devices for just their home, basically, in the next 50 to 100 years. You know, every light bulb will have an IP address. That's already a thing. So this is only going to get bigger. And so when we're talking about the design of these things, we need to make sure that we understand how to make these things scale. So we're going to talk a lot about a lot of different things, but these numbers are not just, to amaze you. They're very important because these are the things that we have to plan for now whenever we write networking software. And again, that is the primary goal in this class. Okay, so essentially, here is some more numbers, and hopefully you can see these. You do have access to the slides, so if some of these are kind of difficult to see, but essentially, most people understand the internet based on the applications that we use on the internet. Basically, a lot of people think that blue E on their desktop is the internet. As a person who used to do tech support, you would be amazed at the different things people think in regards to the internet and things like that. But essentially, the applications that are most popular, things like email. In 2018, we had 1.9 billion people using email. And there were 294 billion emails sent per day in 2018. Today, that number in 2020 is 306.4 billion emails sent per day. Now, note that most emails today do not just contain text. They contain pictures, they contain videos. Basically, there's HTML embedded in these things, and when we learn about how email formats are done, it's pretty amazing that it works the way it does, and it works as well as it does. Remember, as I said, a lot of these protocols that we're going to talk about are from the 70s, and we're doing as good as we can, continuing to use these things. But the ability to start over with some of this would be great. The World Wide Web, basically, where you use a URL and download a web page from a web server. In 2018, there were 255 million websites. This statistic is basically, they say that if you were to try and sit down and spend 2 seconds on every website, you would spend the rest of your life. So there's way more websites than any one human being could ever need or use, and that's just the visible internet. Basically, 98% of the world's internet, or at least this is a statistic I've heard, 98% is not web addresses, it's the deep web stuff where you have to be able to access it with special things such as like Tor or something like that. There's more to it than that, obviously, for those of you who understand, but that's just kind of a quick and general thing. But basically today in 2020 there are over 1.7 billion websites. That's an insane number. There's hundreds of websites for every little tiny thing you could think of. YouTube is a pretty great thing to study in networks because they're so widely used. It's the second most popular website on the internet, period. And so many people use it for their own videos that I may end up, if I run out of space on my phone, I may end up using YouTube links instead of posting on Moodle and just give you the link to that. We'll just kind of see. I doubt it, but in 2018 there were 2 billion videos watched a day, and now in 2020 we have basically 1 billion hours of content watched daily, 5 billion videos. That's 5 billion videos watched per day on YouTube. And we have about 500 hours of video content being uploaded to YouTube per minute. Okay? So 500 hours per minute of video. So we need to be able to talk about scalability and storage and things like that. But once more, we're going to focus on the applications that can support these kinds of numbers. Blogs and Twitter, that's its own thing. You can kind of look further into this as you want. But like Twitter, they're not I haven't found a post in 2019 or 20 talking about things. So in 2018, there were 500 million tweets per day. And tweets are just a certain number of characters, but they go out to a large number of users, and it's a really interesting distributed systems question how to get the tweets from the senders to all the people who want to read it. So if you were to ever take my distributed systems course, you wouldn't necessarily learn how Twitter works exactly, but you would learn the underlying algorithms that they would use to disseminate all this stuff. But that's a shameless little plug for another course. And then lastly, Facebook. We have, in 2019, we had 1.69 billion total users. Notice 2016 had more users than in 2019. So the number of users in Facebook kind of hit a plateau, and now it's decreasing. Basically, Facebook is now considered the thing for your grandparents to use. It's pretty interesting the shape that Facebook has kind of taken. As new generations of computer users come out, less and less, as these numbers show, are using Facebook. They're using other means of social media. So we might see Facebook decline into nothing at some point even. But these numbers are, again, they're important to understand a lot of different things, but I love to show this slide, because this is what the internet through Yahoo looked in 1994. Okay, what you are looking at, and hopefully you can read these, and this is, by the way, something that Akamai, I pulled this picture from an Akamai presentation, but essentially you are looking at every single website that existed in 1994, right? So you had this label of all websites that were art websites. There were 466 at the time. Then we had business websites. There were 6,426. And then, we have entertainment, almost 6,200 websites. But this was basically every single website, okay? And it was pretty much, this is all we have, here you go, take what you want, and this is how you kind of search through the web in the early 90s. Most people didn't, the population at large at this point did not really have, they definitely didn't have access in the home. It was either through business or the really, people that had the money could do dial-up connections. But at this time, it was not a very typical thing for people to have internet access in the home. Some did, but most didn't. But essentially, it's important to look at these things in the past, because if we see where we've been, then we can kind of see where we're going. And something just as simple as getting the URL for a particular web server. You go to Google and you type a search, essentially you say, I want to find the website for XYZ. So once you find that website, or once you find the URL to that particular website, like www.roseholman.com or .edu for Roseholman, once you have that, the number of steps that it takes just to figure out what that IP address is kind of mind-boggling, and we're going to talk about that when we talk about DNS. But essentially, once upon a time, there was this file called hosts.txt, and it contained every single website in existence mapped to a specific IP address, because IP addresses are actually how you find a web server out on the internet. The URL is just for human readability. And so this one file, you would go and download it from some reputable source, and then when you typed in a URL, your computer would do a local lookup on the machine in this host.txt file, find the URL you typed in, and look up the IP address and go from there. This is obviously a bad idea today. It's not scalable because there's so many new websites. You basically have to download this file every time you want to use the internet. So they made it non-centralized. They made it into something where you could do a DNS lookup, and we have the system that we have available today. But there was once upon a time that you literally downloaded a file that stored all of the websites with their respective IP addresses, and that's how you found the machines. And yes, you had to download it whenever you needed to update things and things like that. So we've come a very, very long way in a very short amount of time. As I've mentioned, it took the printing press 200 years from the time it was invented to the time people started accepting it as a viable technology. This is, in a matter of 10 years, went from nothing to this, and then in another 20, it went from this to what we have today. And it's just astounding, and that's why I absolutely love this class and this topic, because it's one of the fastest growing areas in the world. Okay, you definitely can't learn everything and know everything in this area, because by tomorrow, what you know, a lot of it is already even out of date. So I also want to talk about some issues that the internet has, some ethical issues that we have to consider. And there are a lot of ways that the internet can be misused. There are a lot of ways that people can even be controlled through the internet. Now, I'm not a conspiracy theorist, I promise. But there are definitely things that governments can do using the internet to squash certain things. And, if you read in one of the older Akamai reports, basically there are a few countries, I will not name them here, you can look them up, but there were countries that when high school students were going through standardized testing, they would literally shut the internet off to keep the students from being able to look up answers and cheat on these standardized tests. And so the question is, can you actually do that? And the answer is yes, to some degree. Now, if you were to go through this class, you would understand kind of how to bypass that, because basically what they did was they just kind of stopped the DNS system, where nobody has any way of, unless you know the IP addresses of the machines you're looking for, you wouldn't know what to do. But we need to talk about a few of these things. So there was a time back in 2011 when we had the Egyptian government just basically shut down the internet because of basically a response to protests and things like that. And so this is what the traffic looked like up to January 27th at about 5:30, 5:45 p.m. So you had a lot of, this was your basic usage, but right before it got shut off, we have a lot of, kind of a peak of communication here. And this was people kind of talking about the protests and all that kind of stuff. And then you notice a very distinct drop off, because that's when they shut this stuff down. And it's interesting because you still see a little bit of activity here. This basically represents the number of people who know how to bypass this stuff, who understand networks. You, after going through this class, will belong to this very small minority of people who, will not be taken down by their respective government. But anyway, this is some really interesting stuff. Because it kind of just, it makes it more real when you see these numbers. And then, I'm not going to go into this, but basically there was a time when there were a lot of ISPs that were looking at web traffic, and you had a lot of peer-to-peer traffic that companies like Comcast were thinking about, in fact, kind of limiting, because peer-to-peer traffic was causing kind of a bog in the network when it's kind of started taking off, things like BitTorrent, because you have people trading files back and forth. And the internet at that time was kind of made to be, one directional, where you had content on servers and it was meant to be downloaded by a machine. But with this peer-to-peer traffic, what you have is you have one side uploading that's not a normal web server, and then you have another side downloading. And so essentially it doubles the amount of traffic for that singular ISP, because if you have a lot of people behind the same ISP, they're doing a lot of communication back and forth, and there's not even traffic going out. And so it started to bog them down. And so companies were starting to say, okay, we can't handle this kind of traffic, so we're going to throttle it. Basically, when Netflix first came out, okay, understand that it nearly shut down the whole internet. When Netflix first started, it was interesting because the amount of traffic shot so high up that basically ISPs weren't able to handle it. And so there was a big issue with network traffic, because that was kind of the first mass video streaming that people would use. And that uses a lot, these videos are very large files, and so you have like a constant streaming of these files. And so there was a lot that they had to do in the infrastructure to be able to rise to the occasion to handle these things. And we're going to talk about that too. We're actually going to use Netflix as a case study, along with YouTube, a couple of times in this class, especially when we talk about the applications and the Chapter 9 stuff. But there was kind of the government stepped in and said, no, you've got to treat all this stuff equally, whether they're downloading from a web server or downloading from each other. All bits are created equal, as it were. And so this was a big thing once upon a time. This is probably when you guys were very, very young when this was happening, but we have at least benefited from it since. Now, I've already alluded to this a number of times, but basically IP version 4 addresses, we're going to talk about the IP layer of networking and how IP addresses work and how they're converted and where they go and things like that at a later date. But essentially an IP address is just a way to identify a particular machine, a particular connection, shall we say. Not just a machine, because a machine can have multiple IP addresses for each connection. It's kind of weird, but essentially, way back in the day when they were making these addresses, they used 4 bytes, and they thought there's no possible way that we will use or have this many web addresses to account for. And so when they first started kind of allotting addresses, an ISP would request thousands upon thousands of a set or a block of thousands upon thousands of IP addresses, and they just handed them out because they're like, of course you can have this many, because there's no possible way that we'll use all of these addresses. So here, take a few hundred more just on on the house. And so through time, I guess you could call it misuse of IP version 4 addresses caused us to run out a long time ago. And in 1996, they started the effort to turn to version 6, which is basically a 16-byte entity. Let's see, this is this is 1 byte, 2 bytes, so 2, 4, 6, 8, 10, 12, 14, yeah, 16 bytes. I always, for some reason, I can never remember that number 16, but anyway, 16 bytes for an address. So we've been trying to go from 4 bytes to 16 bytes. That's all we've been trying to change. We've been trying since 1996, and we're still not there. There have been a lot of creative things to kind of stretch the version 4 addresses out. Things like NAT addressing, which we're going to talk about in this class as well. But basically, this is where we're headed someday. This is where we want to be with these addresses. But basically, it's a really slow process. But there are no more version 4 addresses. If some new company wants them, they're going to have to buy them off of somebody else. Okay, so another huge thing in regards to the internet is the ability and the capacity for attacks, right? Hacking and all that kind of stuff, which hacking is now kind of taken on a different meaning. At one time, hacking meant what we use as cracking today, whereas today a lot of people use the word hack to just kind of describe the process of just throwing a bunch of code together as quickly as possible, like you hack code, hence the term hackathon for those events. But whether you call it hacking or cracking, the idea is basically once a machine is connected to the internet, it is now vulnerable to people trying to gain access to your files, maybe even control your machine, and it's kind of scary how easy it is to do in some cases. There's a lot of ways that, even though you have lots of security, and you say, okay, I recognize that you're a threat, so I'm not going to do anything, but imagine somebody who has the ability to write a program to access many, many machines at the same time, and them all try to do kind of flood a particular server for a particular request, and you have thousands, maybe even tens of thousands, hundreds of thousands of machines all trying to do as many requests as possible on a particular target server. And so this is what is known as a distributed denial of service attack, where basically just the act of sending in as many requests as possible to the server, even if it recognizes that they're bad, it still takes an amount of time to look at a request, figure out it's bad, and then throw it away. And if you're getting thousands upon thousands upon thousands of those per second, then it really bogs down your ability to be able to service the people who are actually not malicious, right? And so just by being able to write programs that just request things, even though you're not gaining access to anything, you can shut down a whole system. When I was doing my research at Purdue, for instance, in distributed systems, I needed access to a lot of machines. So I ended up using basically every machine in every lab on campus at the same time. And so to do my experiments, I would go to my office about 2 or 3 a.m. In the middle of the night, and then I would look, and they had cameras on all the labs, and I would look to see if anybody was using a computer, and if they were, I would remove that from the set of computers that I would use. But I essentially had this script that accessed every machine on the Purdue campus all at the same time to do to run my numbers and prove that this was faster than that and things like that. And it's amazing how easy it was for me as a student to do this. But I will say I did get a lot of hate emails from people who were working remotely or something like that, and they're like, "Hey, you're thrashing my freaking machine here." Or, and I did get an email from the administration, but I'm like, I had permission from my advisor. He told me to do this, and they were like, okay, just try not to bother other people. So it's once you know how, it's actually pretty simple to do stuff like this. Now, in terms of this course, we are not going to go very deep into security, okay? That is a whole field in and of itself, and it's actually a very difficult field, okay? So if you want to learn about network security, there are other courses here that you can take that would kind of give you this information. We're going to touch on it, okay? Don't get me wrong. We're not going to just completely ignore it, but we're not going to be able to go in great depth because there's just so much that we need to talk about. So when it comes to cybersecurity, network security, we'll talk about kind of the intro to this stuff, but I'll leave it to another course for you to learn the deeper sides of all of this stuff. And basically today you just use some kind of software that people make for cryptography and signatures and all that kind of stuff and public access keys. Most people don't really need to know how that stuff works to use it, to a degree. I'll say that, but it is good to know how it works. But again, we're just not going to do that here. Okay, so I've got just another little bit, and we'll find a stopping place here in just a second. I know I said 20 minutes, but just bear with me for another couple. So when we look at the internet, okay, this is the kind of view that we're going to take, okay? And so this figure here, we kind of have these, let's see here. I'm going to draw a bigger picture here. So we kind of have this thing that we draw, and it's like a circle, and then we put this symbol here, and this indicates we have a router, okay? And so the internal of the network, okay, the guts, as it were, to this whole thing, basically you have a lot of routers connected together that do the process of what's known as routing and forwarding, and those are two different things we'll talk about. But essentially you get a message in and it figures out where the message should go from there. And so we have what is known as the network edge, and that's basically your computers, your phones, all of the devices, but also that includes the servers as well, because the servers are on the other side of all of this stuff. Basically we kind of have the view that there's this internal part to the network where we have all of this routing, And then we have the network edge where you have all of your devices, and they're communicating using the network at large. And so basically, if I have a message starting here, and all I know is I want this message to get from here to this other machine. I don't care what path it takes. I don't care how it gets there. I just need to send a message from here to here, and I'm going to let the network handle how it gets there. And so we're going to talk about the whole process. There's many different steps to this, but we will get there eventually. Okay, so when we talk about the connected devices, okay, we usually talk about these things called end systems or hosts. So when I talk about a host, I'm talking about a machine on the edge of the network. And the hosts are what run the networking applications. The internal of the network is slightly different, okay? So we have, at the lowest level, we have the links, whether it's fiber, fiber optic, copper, or a wireless like a radio or satellite. And this is where we talk about the transmission rate of the medium, which is bandwidth, the most number of bits that you can send over a particular time interval. And then essentially we have, on the inside, we have routers and switches, and there's kind of a minor distinction between the two. Again, we'll talk about that later. But essentially, it was determined that whenever you have a large bit of data to send, it should be broken up into fixed size chunks that we're going to call packets. And it turns out that this was a big win in order to get a fair share of the network. And so by breaking up our data into these things called packets, now the routers, they just simply deal with packets. Everything that comes in is a packet, everything that goes out is a packet. Every packet has a header that has information of where it's from, where it's going, and other pieces of information. And so this is basically the internet in a very, very, very gross summary. But we're going to look at each individual piece, including the stuff that works on the end hosts, the stuff that works. We're going to even talk about the physical layer very briefly and talk about the different kind of transmission media. And then there's a lot of time that we're going to spend on routing and forwarding and how packets get from one place to another. Okay, so, come on. Oh, turned off. Technical difficulties. Okay, so when we talk about the internet, people, again, typically think of the internet in terms of the applications that they use to access it that works on top of the network. And this would be a point where I would ask you, what are some applications or that you use on a daily basis? But, the World Wide Web, that's, a pretty obvious one. That's where we go and search for websites, type in a URL, and download the web page to our machine and display its contents. And then we have email, which is probably one of the oldest applications on the internet, and it's got its own set of protocols and things like that. And the World Wide Web and email work similarly, but there are some distinctions that we'll talk about. And then, you have all these others. File sharing is a big one, whether it's legal or illegal. There, believe it or not, yes, there are ways of legally sharing files. It's just not as widely used, I guess, as the illegal type. But there's so many different applications, and so basically what I want you to get out of this class is I want you to walk away understanding how these applications work so that you could build your own. That's the ultimate goal, to understand the network enough for you to be able to build your own network application that works for this kind of scale, for this number of machines, and it's robust in this way and that way because you understand how this stuff works and how you put it together. And so one of you guys could be the next great application developer to come up with the next application that takes the world by storm, and you become a billionaire. Don't forget me when you do. You know, basically, applications are where it's at. So that's where we're going to basically start and finish in this class. So Wikipedia defines the internet. It's a worldwide, publicly accessible network, basically, of interconnected networks. So you have a bunch of small networks that connects a bunch of or a number of computers locally, and we usually call these local area networks, or LAN, or LAN. And these networks are connected to one another in such a way that now you have machines on one network sending messages to machines on another network through other networks. So it's a network of network of network of networks, if you will. And so basically the book gives an example of an application. This is kind of nice because you see that there's an area where people are drawing things, there's video chat, there's text chat going on. So this application is actually doing a lot of different things, and you know, all of these things require different protocols. Sending text is very different than sending video online, or you know, drawings, and the ability for everybody to kind of see it all at once. So this is a good example of an application. What it does doesn't really matter. It's just people being able to talk and draw things as they go. Okay, so we're going to stop here. So the next lecture will essentially start from this slide, which is slide number 19. And so we will kind of pick up from where we left off here. And I'm going to switch gears now, and I'm going to talk about your Lab 0. And so pardon me while I kind of get set up here. I'm just going to basically type right here. Let's see if I can do this. Yes, I think I can. Okay, so hopefully you can see the screen. If you can't see me, it's fine. But now let's talk about your Lab 0. Okay, so it's basically it's a 60-point assignment where you're going to write 2 files. Okay, so this lab says it should probably be completed in a Linux environment. If you have a C compiler working on your Windows machine, that's fine. Use it. But it's usually a lot easier to get C working on a Linux machine, or install Xcode on a Mac, and you'll have a C compiler that way. However you need to do it, whether it's a virtual machine, on or off campus, on your own machine, whether you're doing a dual boot partition, however it is you choose to do it, that's up to you. My recommendation is typically to use a dual boot partition. But note that takes up a lot of space. With virtual machines, you know, you can kind of grow and shrink the disk as you need to. But with a dual boot partition, you kind of have to specify up front how much space each operating system is going to get, and then they can't be interchanged. So there are a lot of pros and a lot of cons to each of those pieces, or each of those options. And it really is just kind of up to you. But one thing that I would strongly argue is that the ability to work in a Linux environment is very, very important. Whether you're a programmer, whether you're an engineer that writes programs to some degree, you're going to need to know Linux and how to install things on Linux, how to use it, which, you know, it's not quite as user-friendly as, say, Windows or Mac OS, but it's getting better and better. But it's a much more secure environment, because basically, you know, installation is really hard in a Linux machine when you're first learning. It's much more difficult installing things, but the reason for that is what you lose in usability, you gain in security. You know, that works to a certain point. So, you know, I'm not saying that's an absolute 100% in either direction, for those of you who understand. You know, kind of back to the task at hand here. I recommend having a Linux environment, access to it somehow. And I say all of that about Linux to basically say anytime you spend learning how to use Linux and how to do this for this class is not a wasted effort. It is something that I promise you, if you do any kind of programming out in the real world, unless you go and work straight for Microsoft directly, you're going to run into Linux. The ability to do stuff in Linux is a very important skill for anybody who does any kind of programming. So again, this is kind of stuff you'll have to learn on your own. Like if you want to use a command line editor such as Vim or Emacs, yeah, there's a learning curve there, but it's worth learning. I truly believe that. So however much time you want to dedicate to that is up to you. It shouldn't take a whole lot of time to do what you need to do. Basically, you need to have a Linux machine that has GCC installed, and then you need to be able to edit the file and compile it, and that's basically all you're going to need for this course. Anything you do above and beyond that is still to your benefit, though, and I would strongly argue that. Okay, so first things first, what you're going to do is you're going to download the files, and right now it's hidden to you. That's what these blue things are. You won't see that when it's shown, but essentially you'll click on the Lab 0 Download Me link, and you will get a zip file. Okay, and this zip file will contain the following files. First of all, this XLS file is kind of a rubric. Okay, it's a very general rubric for this program, so you can kind of see how we're planning on grading this. Okay, and then you'll have two C files, paint.c and palindrome.c. These are both standalone. They don't work together to make one program. These are separate programs. Okay, and so here, you should be able to see it a little bit better now. So paint.c is its own program, and the make file is going to generate a runnable called paint. Okay, and then you run paint. And then when you run make, it will also create an executable called palindrome for the palindrome. So basically the two programs you're going to write are in this, and I'm going to quickly discuss make files. Okay, now those of you who understand make files, you know that it is a very large topic. Okay, we simply just don't have the time to cover all there is about make files. But essentially, you can compile code from the command line. For instance, let me go into my solution here. Okay, so you can see I have a make file, I have paint.c, and I have palindrome.c. So if I go in and I look at the make file, okay, actually let me back up. So let's say I want to compile paint.c and make an executable. Okay, I can do that from the command line like this. I can say gcc, that's the compiler, and then I say paint.c, and then basically if that's all I type and hit enter, I'm going to have a runnable called a.out. So if I don't specify the name, it's always a.out, and I can actually run this by saying /a.out, and that runs the program through the command line. But the problem is now let's say I want to compile palindrome, so I say gcc palindrome.c. When I do that, it overwrites the a.out, and so now if I say /a.out, it's going to run the palindrome. And so I needed a way to make different executables. So the way to do that, I'm going to remove this a.out so I don't have it. The way to do that, like say for paint, I say gcc paint.c, and then I say -o, and then I give the name of the executable. In this case, I can call it paint. And so this command, and as I mentioned in class before, make sure that whatever you write after the -o is not a file that already exists, because it will overwrite it with the executable. right? So if I were to say -o paint.c, it would put the executable inside of paint.z and I would lose it. You know, when you're working on the command line, there's no Control-Z stuff here, guys. So, you know, you want to be very careful. The changes are instantaneous and they are permanent, and they usually don't even ask. There's no, are you sure? You know, it just does it because it assumes you know what you're talking about. So this will create a runnable called paint. And so if I list the directory, I now have a runnable called paint, and I can also do the same thing for palindrome. -o palindrome, not .c. That's where your tab character can, you know, kind of mess you up because the autocomplete if you're not careful. But anyway, so I say that, and now I have two runnables, okay? Now, your job is to follow the instructions for both paint and palindrome, okay? Oh, sorry, makefile. Let me go back a step. So, any project you can compile from the command line, but it's, you know, the bigger the project gets, the more typing it involves, and usually, you know, it's going to be a very large command, and you can find it by hitting up and down in the command prompt. But there's definitely got to be a better way, and there is, and that's where the makefile comes in. And these things are very complex. I'm not going to lie. There's a lot to understand here, and you can find a million different makefile tutorials. But I'm going to try and provide you with as much stuff that you need, where it's just basically going to be a copy and paste for you. And then later on, I'll provide you with a generic makefile where you just change like literally 2 lines and it will work for any project. So if you don't feel comfortable with makefiles, all you really need to know is how to use them, and I'll try to provide the rest. Now there is a little bit for you to do inside of this makefile, but there's not much. So let's take a look. So I say vim makefile, and so basically these top 3 lines, okay? CC is the, no, this is not the one you want to see. You want to see this one. Yes, this is the one you're going to see, okay? So, up here at the top, so we have comments using the pound sign, or the hashtag sign or whatever. So you can have comments in a makefile, and so I tried to comment this basically, you know, as straightforward as possible. But there are a few like key things here. So here we have this all colon. And so what that means is these are all of the files that you are going to create, the runnable files. And so notice I have one called paint and one called palindrome. And so whenever the compilation finishes, it will create 2 different runnable files, one called paint and one called palindrome. Now, notice that lines 5 and 6 and 9 and 10, those are how we compile the paint.c. Now, it's going to look kind of odd because what this says, this rule says for the paint executable file, you need the paint.o. And that's an object file. And this is how you get paint.o. You compile GCC saying paint.o -o paint. Okay? And so basically what this means is it takes an object file called paint.o that's created from this line down here, and it makes an executable from the paint.o. So we have an object file, and so line 6 is compiling, as it were, or creating an executable from the compiled object file called paint.o. And so notice here we have the -o, where this now says, okay, whenever you create the executable, I want it to be called paint. And then lastly, we just have some compiler flags here. The -g and the -wall are probably going to be in everything. I included the -lm, and that's if you're going to use the math.h library. If you use any of those functions, it's kind of odd. It won't work unless you have this compiler flag, which links you to the math library, okay? So basically what does that mean? It just means that this -lm is needed if you use any of the functions in the math.h uh, file, which is a series of functions like ceiling and absolute value and you know, basic math functions that you don't want to have to rewrite yourself. So this line, these lines down here, lines 9 and 10, this says how to create the object file called paint.o. And you use paint.c to get there. And so that's what line 9 is saying. In order to get paint.o, you need the following files. And so when you're making a project with multiple files at the same time, there's just going to be, it's going to be a number of files separated by spaces. And then you have the compile command that says, I want you to compile paint.c. The -c command says, create an object file, compile it into an object file, and then we have the same -g, -lm, and -wall with a capital W. So arguably lines 9 and 10 work or happen first, okay? You know, so there's kind of it's a reverse order to this thing. Notice up at the top we have the final result. We have the next to the last step and then the first step. And so basically you can kind of think of it as working backwards. And so lines 9 and 10 are what happen first, where you take paint.c, you compile it into an object file called paint.o. And then once you have that, you create the object or the executable object called paint using paint.o. And so this takes the object file and turns it into a runnable. Now, you are going to need to do the exact same thing. Oh, very important. This right here is not spaces. It is a tab, okay? In Makefile, if you don't, like, if you don't indent, it's not going to work. And if you use spaces, you will get some weird errors. And so line 5, there's no spaces or tabs in front of it, but line 6, there is a tab in front of this because the Makefiles are just very, very, very picky in that regard. I'm not going to go into the whole explanation as to why, but essentially all you need to do to get Palindrome to work is copy and paste this thing and change the word paint to palindrome, and essentially you're done, okay? But I just kind of wanted you to have the practice of getting that stuff working. Now, for the palindrome, you will not need the -lm compiler option. You don't need the math library for a palindrome. Okay, so you're going to add your stuff here, and then notice at the very bottom we have this clean. And so whenever you want to compile, you just simply type make, and that compiles everything. It creates the executables. But there are sometimes you want to just kind of like start all over, and so this clean directory or this clean directive, essentially you'll say make clean, and it'll run this command where you remove all the object files and all of the runnable files, and so you end up with you know, kind of a back to your directory. So here, let me clear this out. So right now you see that you have a make file, and it has to be capital M. You have your XLS, and you have your paint.c and palindrome.c. Now, once you have the make file, which the make file is already working for paint.c, and it creates an empty, basically useless palindrome executable. It's up to you to define how it compiles and creates it. But essentially, to compile things, you just simply type make. All lowercase, you say make, hit enter, and it will compile everything. Now, notice right now, it's giving me an error, or a warning, not an error, and it's saying the linker that you're using to the math library is not being used. I just want you to make sure you understand this. You know, but that's because this file, if we look at paint.c, it's a very empty file, right? It's got some includes where I have the stdio.h for input and output, and then including the math.h, which is the math library. Now, inside of this code, you'll notice that there's a main. Your code goes there. Now, I have already defined 2 function prototypes, and the way you have to do functions in C is you either have to define them before you use them, okay? Like if at the top of the file, right under your includes, if you write the functions, they can be used anywhere under it, okay? But if you want to kind of have main at the top, and the other functions, what you do is you provide these things called function prototypes, which look a lot like something like a Java interface kind of declaration for methods. But basically you give the return type, the name of the function, and then the list of all the parameters separated by commas, and then it ends with a semicolon. Right now it's commented out. I included these two function prototypes for your use as you see fit. You do not have to create, or you do not have to write out these methods, but if you wanted to, all you have to do is uncomment the prototype, and then down here, essentially you can define the function like this. And so you start filling in your code here. So read dimension, this is basically my idea for taking input from the user for a specific dimension. And so I used a char star name so that I can pass it width. And so it prompts, say, you know, give me the width or the height or the depth, you know, and things like that. And so it's just a generic function to prompt the user for input. And then we have the CALC area, calculate the area given the width, the height, and the depth. You can do all of this in main. Learning how to get input from the user using stdin, you can use getLine, or you can use fgetS. You can look those up, and their use, just Google getLine examples or fgetS. That's, let me spell that out, fgetS. Okay, that's a function which gets input from wherever. If you specify stdin, that takes it from the command line itself. So you can use fgetS. GetLine is a really interesting command that like came in the stdio back in like 2010. So it's fairly new. But it can be kind of confusing, and I don't personally use readline in paint.c, okay? All right, so that was paint.c. Now, I just want to quickly show you palindrome.c. So there's a few other libraries. Now, here we have stdio and stdlib, standard library. This third one, line 7, stdbool.h, it gives you access to this type called bool, right? And it's a true or false. It's just a library for your use if you so wish. You don't have to use it. And then ctype.h is where we get definitions for other types, such as this size underscore t, okay? Now, I'll get to that. But basically, I included two function prototypes and a description. So readline is a function, and you can choose to change this, right? Notice it takes a char star star, and the reason why I did that is because the readline function actually requires a pointer to a character pointer, okay? So char star star, that is a pointer to a pointer, okay? So you have a char star, which is a string, okay? And we saw how to deal with strings on the day that we demoed C, but this is a pointer to a string, okay? And the way you can do that, and I talk about it, is basically inside of main, you can say read line. Well, here, let me first say char star string. And this is input you would get from the user, but I'll just set it to something here like hello. Okay. Now, read line. To use it, to turn the char star, which is, you know, the string, or the variable called string, to turn that into a char star star, you just pass it the address of string. And by passing the address, you use the ampersand. That is the ampersand symbol. Let me get really good in there so you can see that. So we have the ampersand symbol in front of string, and so that's saying send the address of this variable. Well, the address of this variable is another, what's located in there is another address, right? So it's a pointer to a pointer. Why it uses that, it's a little bit beyond the scope of discussion here. So if this confuses you, just use fgetS. Don't worry about readline. Readline's nice, but don't worry about it if it confuses you. You can use whatever you want. You're not forced to use anything. So the two functions that I defined are readline and isPalindrome. Again, you can do whatever you want with this lab. You can put all the code in main for all I care, and as long as it works, it's great, okay? But there's a few things you need to remember. First of all, when you're getting input from the user, the very end of that input is going to be a new line character, okay? So when you use readline or fgetS, when you get input from the user, when they hit enter, you get all of their data plus the new line character, the \n. And so what you're going to want to do to handle that is remove that \n at the very end of the string. It's just the last character of the string. Remove the new line and replace it with a \0. And so that indicates the end of the string. And so you're going to have characters separated by spaces, and then as soon as you see the \0, that means that's the end of the string. And so that's how you can use a lot of the different string libraries and all that kind of stuff. Okay, so with all that said, I'll give you a demo. I'm just going to exit this without saving. So I'm going to demo the two programs, okay? Now, what are they supposed to do? Well, paint.c is you're going to be given you're going to request from the user the dimensions of a pool, okay? P-O-O-L. You're wanting a program to calculate the amount of paint it requires to paint a pool, like a swimming pool, okay? And so essentially when you run paint, let me go into my runnable here, lab 0 solution, okay? First things first, you run make, okay? And that compiles everything. And now I have a runnable called paint and a runnable called palindrome. Okay, so when I run paint, it doesn't need any arguments. You just run it, and it's going to ask for the width, okay? Now, this is not don't worry about it being one of those pools that goes from a shallow end to a deep end. Just assume that the pool is completely uniform. So let's say that the width is 20 feet, okay? I hit 20 and enter. The next thing it asks for is the height. Let's say that the pool is a 10-foot deep pool, okay? Height is not the, height is, so we have width and height, which would be kind of like if you're looking down. So let's say that this pool, from one end to the other, it's 20 feet wide and it's 60 feet long. So the height would be the length, sorry for that confusion. And then I hit enter, and then it asks for the depth. So let's say that this is a 10-foot deep pool. Now, when I hit enter, it calculates the total area, which is 4,000, and then it also calculates the number of cans of paint required to paint this amount of space. Now, you'll notice that what I basically did, and I even give you in the lab description, I give you the formula to use, which is basically the formula for the surface area of a cube. Now, those who are paying attention and are very astute here would notice that when you have a pool, there's one side that's missing, right? When you think of the surface area of a cube, it's an enclosed thing, and a pool doesn't have a top, okay? Now, it's okay for you to use the surface area of a cube, and basically my way around that is saying, assume you have to paint the cover of the pool, which is the same dimensions as the floor of the pool, which gives you a total cube. Or, assume you need a second coat on the floor, and so basically all you need to do is get the width, height, and depth of the pool from the user in the same way that I showed you. and then use this formula to calculate the total surface area in terms of feet. From there, you calculate how many cans of paint you need. And notice that I tell you that 1 can of paint covers 200 square feet of a wall. Okay, so if you have 4,000 square feet of surface area, as we have here, then that divided by 200 gives me, and remember to take the ceiling of the rounded value, because, if it's 19 and a half cans, you'll essentially have to buy 20 cans. And so 4,000 divided by 200 is 20, and that's how many cans of paint you need. And basically, notice that it does not loop. You run it once, and you get one result. You have to run it again with a width. Let's say that now we have a 50 foot wide and a 150 foot long, and let's say the whole thing is only 8 feet deep. I hit enter, and I get a total area of 18,200 square feet, which would require 91 cans of paint. Okay, so that's all you have to do for paint.c. Once you get this, I gave you some example input, output. Now, you can either do the surface area of the cube and be done with it, or if you want to go the extra mile and remove the top side, I'm okay with that, whatever. The graders will be merciful in that respect and count either one of them correct. Now, palindrome is the other thing that you're going to have to write. And if you don't know what a palindrome is it's essentially a word that is the exact same forwards as it is backwards. Okay? So, for instance, the name Anna is a palindrome. Okay? Because it's spelled the exact same way forwards as it is backwards if you don't consider capitalization, right? Which you need to handle both cases, whether, you should ignore case by converting it to all lowercase or something like that. But you should be able to determine a palindrome by ignoring case, and you should also ignore all special characters such as spaces, exclamation points, question marks, and you should also ignore numbers. And so you only look at the letters in the string, and there's actually a function I tell you about this in the lab. Okay, I tell you from the C-type library, you have this function called isAlpha, where you pass it a character and it returns true or 1 if it's a character, A through Z, whether capital or lowercase. Anything else, it will return false. And so this is the only function you need to worry about to make sure that you're only looking for the palindrome in terms of characters. Now, what you're basically going to do for the palindrome, here's some example output. You're going to keep looping. Okay, now this one, if you don't keep asking for input, if it only runs once for the palindrome, you will lose points. But essentially, if I run palindrome, okay, it asks for a word, okay, or it says word, but it really it should include spaces. So let's say the word best. That is not a palindrome, okay. It is not spelled the same forwards as it is backwards. So if I hit enter, notice it puts best in quotes and it says best is not a palindrome, okay. And so your output will either be the word is a palindrome or the word is not a palindrome. And you're going to keep looping. And so I have some other things here. So like the name Anna, like I said. Now notice I have capital A, lowercase N-N-A, and I hit enter, and it says Anna is a palindrome. Now, there's this really good tester right here that is a palindrome, and it's a whole sentence, and I just copy and paste it. Go hang a salami, exclamation point, I'm a lasagna hog. Now, notice, you should be ignoring spaces, you should be ignoring case, and you should be ignoring the exclamation points. And so, you're just wanting to determine if the letters are spelled the same forwards as they are backward. Now, that means the first half of the string appears in the latter half backwards. You know, however you want to do that. Recursion works great for this. You can solve it however you want, but I hit enter and it says that what I entered is a palindrome, okay? And I can keep going. I can say AAA, BBB. Now that backwards would be BBB, AAA. That should be a palindrome, okay? And so on and so forth. So that is your lab 0, okay? And I'm sorry that this video was particularly long. I promise that in the future these videos will be almost right at 50 minutes exactly. This one was just kind of trying to do a lecture and a lab together. And to stop, you enter the character of a period. If you enter a period and hit enter, that should exit the program. All of that is in the instructions, but I just wanted to be clear. So there's your demo for Lab 0. You have a week to do these two programs. Again, once you get the C stuff down, it should not take more than 30 minutes for the whole thing, okay? So, you have paint, and you have palindrome, and you have a week to do it. Now, at the end of this first week, we will have another lab, and so I suggest getting this done as soon as possible, because the next lab is going to be actually like doing sockets and stuff, and that's significantly more complex than this. So just kind of warning you ahead of time, I would try to get this done as soon as possible so that at the end of the week when we have Lab 1, Lab 0 is just kind of an intro lab to get things started. Lab 1 is where things start kind of getting serious, and it's based on the material and all that kind of good stuff. Okay, so that is all I have to say for this video. Again, this is the first one, so there's a lot of kinks here. You know, you probably, like, I don't even know if you can see me. This is just my first run through. They will get better as we go, but as you run into questions, again, you should utilize Piazza, and if you must include code for your question, please limit the amount of code to just a couple lines, because remember, if other people are being able to see this, you might be giving them an answer to something that they were struggling with unintentionally. So if you need to send a lot of code, just email it to me or take a screenshot, whatever, and I'll take a look at it from there and try to help you out. If it's something we need to discuss stuff, like we can do Skype, we can just talk over the phone. I have FaceTime if you have an iPhone on both my computer and my phone. However you need to get answers to your questions, you can text me. You know, the best way to start is through text, right? You can ask a question, and then I can say, well, we should probably talk about this in person. And so we can set up like either a phone call or a face-to-face digital thing or whatever. Funny enough, we're even going to learn a little bit about how Skype works. You know, so if we're using Skype, you'll know what's kind of going on under the scenes to a small degree. So when you run into questions, simply ask them as soon as possible, and I will try to keep up with email. We'll have the TAs and the students looking at Piazza, and I will definitely keep track of text through the phone and all that kind of stuff. So you should have access to get the answers to your questions, and you should be able to get it quick. If you're stuck for more than 30 minutes on something, it's time to get help. This kind of stuff does not work very well, just trying to change random things and then hoping that works. When you run into a segmentation fault in C, it's kind of ugly. That is basically any kind of runtime error. When you run into that in Java, it's a nice thing. It says array index out of bounds exception, or it tells you the kinds of things that went wrong. In C, if you do an index out of bounds, if you do memory mismanagement of any kind, it just simply says segmentation fault, and you might have to like put print statements throughout and figure out where the segmentation fault occurred, and then figure out how to fix it. So there are some things that you're going to run into that may take some time, especially when it's dealing with segmentation faults. So if you're stuck, get help soon, okay? And that is all I have for this video, and I will see you guys in later videos. So hope this video works. I hope you can read this. Please give me input if it doesn't. Please tell me if there's something wrong, and I will try my best to fix it. Otherwise, sorry for the long video. I'll see you guys in another one. Over and out.